Last thing we need to do with congruent triangles is deal with triangles that are on a coordinate plane. So if we want to prove that triangles are congruent and on a coordinate plane, that opens us up to use more tools because now we can use our distance formula, use midpoint formula, things like that that we couldn't use before. So I'm going to go over the different ways that you can prove triangles are congruent on a coordinate plane. All the same possibilities are there. So you can do side angle side, side side side. Um, you can't really do angle side angle or angle angle side because really the only angles you're going to be able to figure out are right angles. Okay, and the way we'll figure those out is by looking at slopes of lines. So I'm going to list all the stuff that I can get using the different tools I have, and then I'll show you which ones to pick out to help you get congruent triangles. So on this first triangle, ABC, I can find the length of each side with the distance formula. So actually I don't want segment AB, I want the length of AB. So AB is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, AB is actually easier than that because it's on a nice horizontal surface for us, so I can just count the squares. 1, 2, 3, 4, 5. AB is 5. Okay, I can do the same thing for BC. BC is 1, 2, 3, 4. AC, I can't count the squares because this is not 1. Okay, it's actually the square root of 2. But a diagonal is not the same length as a side, so I need to use the distance formula. So A is at negative 1, 2, 3, 4, 5, 6, 7, comma, 1, 2, 3, 4. C is at negative 2, comma, 1, 2, 3, 4, 5, 6, 7, 8. So my distance formula is going to look like this. I'm going to take negative 2 minus negative 7 squared plus 8 minus 4 squared. So this turns into negative 2 plus 7, which is 5. 5 squared is 25 plus, this is 4 squared, which is 16. Okay, so now I get 41, square root of 41, which doesn't break down because it's a prime number. So AC is square root of 41. I can get that. It looks like this might be a right angle, so what I want to do is I want to check to see if that's a right angle. So the slope of AB would be 0. The slope of CB would be undefined. Those are perpendicular slopes. And I'll show another example next where we can see right angles with different slopes. For right now, I've got all 3 side lengths of this triangle. I need to find all 3 side lengths of this triangle and see if they match, because then I'll have congruent triangles by side, side, side. So DE is 1, 2, 3, 4, 5. Okay, EF is 1, 2, 3, 4. And DF is going to require distance formula again. So D is at 3, negative 1. F is at 7. Negative 1, 2, 3, 4, 5, 6. Okay, so subtract my x's. 7 minus 3 is 4 squared. Subtract my y's. Negative 6 minus negative 1 is the same as plus 1, so that turns to negative 5 squared. So I get, oops, I get 16 plus 25 again, which is still the square root of 41. So I've got 5, 4 squared root of 41, 5, 4 squared root of 41. So these triangles are congruent by side, side, side. Let's rotate one to take a look at our slopes for finding slopes here. So let's just rotate this, put it on a point. There we go, just like that. So let's say I want to do side angle side. So at this point, I'd have to do distance formula to get this side, distance formula to get this side, and then I want to see if this is actually a right angle like it looks like. So in order to find right angles, we're going to need to know the slope. The slope of this line is down 1, 2, 3, 4, 5, and over 1. The slope of this line is up 1, over 1, 2, 3, 4. So up 1, over 4. These are not reciprocals of each other, so this is not a right angle. Okay, so I couldn't do side, angle, side. I'd have to do side, 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 because I don't have a right angle here. And those are the only kinds of angles we're going to be able to find. Really, this should be a right angle. Maybe I didn't line up my points correctly. Yep, the way it sits now, it's not a right angle. So I couldn't do side, angle, side. Let's see. The other thing we can do is we can use our congruent triangles. Okay, and use our CP/CTC to get certain things. So if it's telling me that these triangles are congruent, okay, so FGI, this one, is congruent to HGI, this one, then I know that all the parts are congruent, okay? So I would know that FI is the same as HI, which lets me know that I is the midpoint of FH. So I can use that to find the coordinates of I. So F is at negative 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's F. H is at 1, 1. So the midpoint, I'm going to add my x's and divide by 2. I'm going to add my y's and divide by 2. So you get negative 5 halves, or negative 2.5, and here I'm going to get 4.5. And that would be the coordinate of I. Okay, so that's another tool we can use when we're on a coordinate plane here. So I just want to demonstrate why the diagonals don't count as 1, and also just kind of review the Pythagorean theorem. So if I draw an isosceles right triangle with legs equal to 5, that means I want to go 5, 1, 2, 3, 4, 5. And it's going to be easier if I just go 5 the other way. 1, 2, 3, 4, 5. So now I've got a right angle and an isosceles triangle because I made these both 5. So if I draw in my hypotenuse, okay, which is a little off. Okay, something like that. One, two, three, four, 5. There we go. Okay, now I want to find the length of the hypotenuse. Well, Pythagorean theorem says a squared plus b squared equals c squared, where a and b are the legs of a right triangle and c is the hypotenuse. So I'm going to have 5 squared plus 5 squared equals c squared. This is 25 plus 25, which is 50. That's what c squared is. I want to know just c, so I'm going to square root both sides. So I get This is 25 and 2. This is 5 and 5 and 2, so I get 5 square root of 2. That's what C is. So an isosceles right triangle, whatever your sides are, you're going to take that times the square root of 2 to get the other side.
High school teachers, if you are